Morning, everybody. Can you see my screen?
We do. Yeah, we see the slide overview on the left too, so you're not full screen, but there you go. Looks great.
Well, yes, thanks so much for having me. I've been attending these for a long time. It's a great talk series, and today I'm going to be talking briefly about me. I'm Mohit Dubey. I'm a PhD student at UC Berkeley with Tina Chow and Sebastien Biraud. And today I'm going to talk about some of my more recent work on estimating basin scale methane emissions using a new type of dense, low-cost solar spectrometer network. And this work is really in collaboration with Josh Paul, who founded a company called Butterfly Photonics, which is building the sensors, and then my collaborator, Aaron Meyer, who's helped tremendously over at the University of Utah. So since this is a pretty methane savvy group, I thought I'd just kind of skip over. You all know that methane is a big problem. It's a greenhouse gas with a huge GWP compared to CO2. But maybe you were not aware that, in the past few years, we've had all these amazing advances in satellite technology with, private companies and public enterprises all putting up new satellites. But there's still this very large gap in the methane sensing world. And what I like to think about this gap as is about the basin scale. So, for large scale leaks at kind of global scales, you have these satellites which can, measure large areas, but their detection thresholds are very high. And then if you want to measure things down, on the order of kilograms an hour, you have all these great ground-based technologies, but it's hard to scale those up. So the question is, how can we start to monitor things like these basin scale regions? And one proposal we have is this idea of a butterfly solar spectrometer network, which I'll talk to you a lot about today. So if you look at the current methane sensing modalities, this is coming from the recent APS report back in 2022, I believe. You have these ground-based things that are autonomous, continuous, and then satellites. These are but there is still this, major gap in these modalities. So one thing that's been around for a very long time are a type of measurement called a solar tracking spectrometer. And the first kind of major solar tracking spectrometer network was the TCON network, which was started in 2004 by Paul Wenberg at Caltech and has been growing ever since. And now there's about 23 of these TCON sites around the world, and each one of them is using a very highly calibrated Fourier transform FTIR spectrometer, each of which costs about $1 million, unfortunately, and are quite tedious to run, but can get very, very precise total column values for methane, CO2, and other trace gases. And now, with these sites throughout the world, TCON is actually very good because it can provide, complementary data to in situ measurements and is actually used to calibrate a lot of these new satellites going up. The problem now still being is because they're so expensive and hard to operate, they're still pretty sparsely placed around the globe and cannot provide something like a basin scale measurement. So more recently, another network has come up in the past, 10 years or so, doing similar measurements with a slightly less expensive sensor, the Brooker EM27 Sun, which goes for about $150,000 a pop. And right now there's about 120 of those around the world, but more and more all the time. And they're doing a very similar measurement. It's taking a, total column measurement of the amount of methane in the atmosphere between the sun and the sensor. And because these are slightly cheaper and have been able to, and are smaller and compact, they've actually been deployed on field campaigns where we've seen multiple of them in one given area. So this was most famously done, Jones et al. In Indianapolis, where they got together 5 of these EM27 Suns, deployed them throughout the city, one was moving around, four were fixed. And using these five EM27 suns and some inverse modeling using Whorf Stilt, they were actually able to, measure and monitor sources of methane and kind of create this city urban scale network that could monitor methane for for a large enough region. So coming from the conclusion of the paper, they said, it will be essential to employ innovative transport models and a diverse set of instruments, including ground-based total column sensors. So they kind of proved this concept that we can use a dense network of these types of measurements to try to monitor these larger scale areas. And this has since been repeated in other cities, including Beijing, Tokyo, and Hamburg. So what we've done here at Butterfly and in collaboration with Butterfly is basically create another version of this total column spectrometer, but using telecommunications parts, we've been able to drive the cost down from $150,000 a sensor to now, if we were to make 500 of them, the bill of materials would be about $2,000. Obviously, it would cost more than that. But this is kind of the key concept here is that we can actually now see these being deployed at a much denser resolution because the cost is so low. So it's based on using fiber optics. So there's actually no laser involved. The sunlight comes in and we use a photoreceiver with a microetalon to tune the we tune it to exactly the right wavelengths where we want to observe methane. And it's because there is no laser, it's robust, there's no chance for misalignment. And our main competition for a similar type of spectrometer is you could use laser heterodyne spectroscopy, and that's actually been done by a couple different groups, but which has the advantage of being much higher resolution. The problem being that that also then becomes more expensive and complex and has less spectral coverage. Actually, with this, you'll see in a second, get a few different bands, and we can actually measure both methane and CO2 with just a single microetalon. So far, we've built three of these cloud-connected prototype sensors, which you can see here at the Butterfly headquarters in Redwood City. And they have nicknames. This is Ren, Stimpy, and PTM, but for the sake of this talk, they'll be STS 1, 2, and 3. And what each sensor does is it turns on, it tracks the sun, and at 0.08 centimeter inverse centimeters spectral resolution, we measure spectra in the range, in the 1600-ish nanometer range, where we can measure methane and CO2 at 1 hertz. So those 1 hertz spectra are collected on board, but that's kind of overkill. Like that's way too much data. So we actually on board, we average those to minute-long spectra. And then we've set up a data pipeline using Amazon Web Services to upload these spectra to the cloud every minute. And actually, we perform all of our analysis in the cloud using EC2 instances. So those spectra are uploaded to the cloud. We linearize the wavelength scale using known methane and other lines coming from the HYTRAN database. And then we fit those spectra using actually the same exact software package that's been developed for TCON. It's called GGG. And following one shed all, we actually then use because we have water lines in our spectra as well, we can use the measurements that we get from our spectra for water to calculate the dry air mole fractions of both methane and CO2. So here's what this kind of looks like in operation. Here is one of the butterfly sensors on a rooftop. And when you turn it on, it automatically finds the sun. And then throughout the course of the day, we'll track the sun and collect those spectra and upload them to the cloud. And from that output, we get these kind of spectra. So as I said, we get a wavelength region from about 1600 to 1660 nanometers, which gives us this really nice CO2 band down here, kind of this empty gap, and then a nice methane band up here. And in red up here are kind of what we would expect to see the simulated lines coming from HITRAN. So we can see that those line up pretty well. And when we run that through GGG, which you see down here, we can see each of these lines corresponding to green being methane, red being CO2, blue being solar, and our residual is overall pretty low and doesn't have really kind of a curve or anything wonky that we wouldn't want in there. So this spectral fitting code, I should note, has been developed for our FTIR spectra. So we're actually working to further refine it and improve it for our spectra, but we're actually getting some pretty decent results for just, using it out of the box. And so now that we can collect these spectra and uh, fit them, we should be able to actually back out some, concentrations of methane and water and CO2. And this was from a field campaign we did back in 2023 before we got a NOAA SBIR grant this past year. And what we did is we set up a butterfly on a rooftop next to two different EM27 suns for a couple of days and just wanted to see, hey, what do we see? And this was before we actually were looking at that lower CO2 range. So our CO2 data is pretty bad. But if you look, the blue is the EM27 sun and the black is the butterfly. We actually see some pretty good agreement there. And we see some pretty good agreement with water as well. And we actually got very lucky on this day, August 9th, where we actually, saw a pretty large enhancement in the methane signal. The winds must have lined up from a landfill upwind. I'll actually show some wharf stilt measurements in simulations in a second. But we basically found that the butterfly was able to track this enhancement in the methane very well. So since then, we've done a lot of work on these prototype spectrometers through a great grant that we got through NOAA. And what we've been able to do is first, we updated how we were collecting the data. It was a little bit clunky at first, and we wanted to streamline that. And then we also made some serious hardware upgrades in November to just improve the overall tracking and the way the spectrometers work. And so for the past 4 months or so, we've been running these spectrometers and collecting a lot of data um, here in the Bay Area where they're based. And I just wanted to share kind of some of those results with you as well. So what we can see here is here's an October, and each one of these different colors is a different spectrometer, and these are each different days where we had data, methane, CO2, and water. And what you can see is before we made these hardware upgrades, the spectrometers roughly are agreeing with each other, but there is still quite a bit of drift, and we wanted to improve those things. So we saw after we made our hardware upgrades that those discrepancies got a lot better. And here's kind of a zoom in on a few more of these good days of data. And what you can see is that on a given day of data, the uh, spectrometers are really tracking each other well for the methane and CO2 and really well for the water data. So this makes us hopeful that, you know, we're getting the type of accuracy that we would need to deploy these at scale and measure some meaningful signals. And here's some one-to-one plots just showing that same data. On the left, we have methane for two of our our two best spectrometers and CO2 for the two best spectrometers. And we're seeing for methane, we're seeing about a plus or minus 5 to 10 ppb enhancements or accuracy, and on the CO2 we're seeing plus or minus. a ppm, which we expect to improve with updated fitting algorithms that are more tuned to the type of spectra that we're using. So where is this all going? Well, now that we have a lot of this types of data, our goal is to eventually deploy these at something like a basin scale. And here's a great visualization that my colleague Aaron made at, this is of the Uinta Basin, but what you can imagine is each of these points on the ground is a different spectrometer, and they're distributed throughout this entire basin. And on the ground, you kind of have some heat map or inventory expectation of where the methane is coming from. And using these total column observations, sweeping the sky throughout the day with some inverse modeling, you can actually estimate where those emissions are coming from. So, like I said, that's still very much in the preliminary work right now. Based on the measurements we took in Utah, we did some preliminary stilt modeling to kind of estimate where that big methane spike we saw came from. And we, based on the winds of that day, could kind of pinpoint that it was coming from this direction. But unfortunately, we only had one spectrometer running that day, so we weren't able to measure, upwind, downwind, or gradients like that, which is what we hope to do in upcoming field campaigns. And another upcoming goal is to try and deploy these throughout the Bay Area on rooftops of schools in collaboration with Ron Cohen at UC Berkeley to kind of have an urban type butterfly network similar to the one that we're doing in the Uinta Basin. So kind of in summary, we see that the butterfly sensor can be actually a really good complement to we're not trying to replace any of the existing great advancements in satellites or ground-based measurements, just add kind of a new piece to this telescoping puzzle of, measuring methane emissions across scales. And at the cost, that we're proposing, for the price of a single satellite, we could deploy about 40,000 of these spectrometers, which would be a huge undertaking, but could help provide, a more continuous way of monitoring large-scale methane emissions. So here's some quick, prototypes of our upcoming version 2, which we have in the works, and I'm happy to take any questions.
Okay. All right, can everyone see my screen?
Yes, looks good.
Okay. All right. So hello everyone. My name is Yuanrui. I'm a PhD candidate from the University of Texas at Austin. So today I'm very happy to be able to have these opportunities to present my work here. So we will be diving into the topic, the geospatial life cycle analysis of the greenhouse gas emissions of U.S. liquefied natural gas supply chains. Oops. One of the reasons I find this topic is so important is because of rapid global LNG trade expansion and its associated climate concerns. So natural gas has been widely used as a bridge fuel to energy transition, especially in the form of the liquefied natural gas. According to the EIA report, the global LNG trade has experienced a rapid expansion during recent years. From 2015 to 2020, the global annual liquefied natural gas trade volume has increased by 45%. So this rapid expansion primarily results from the liquefaction capacity additions from the Australia, the United States, and Russia. By the end of the September 2024, the United States ranked the first for its existing liquefied natural gas export capacity. So, however, since the main component of the natural gas is methane, which is a potent greenhouse gas, a small leakage of the natural gas along the LNG supply chains would result in a significant environmental impact and destroying the benefits of using the LNG compared to the traditional fossil fuel. So therefore, it arises many people's interest in studying the life cycle GHG emissions associated with LNG supply chains, especially the US LNG supply chains. With the improvement of the measurement technologies, some of the recent field measurements across oil and gas production facilities found that the official inventories always underestimate emissions. In one of the paper published on Science, the facility scale methane emissions measurements are conducted over US 9 basins, and the results of this study show that the measured methane emissions is about 60% higher than the US EPA inventory estimates, because the inventory meets the emissions released during the abnormal operation conditions. So not only in the US, the same problem of the inventory underestimation can also be observed in the Canada. A study indicates that the total methane emission measured by the aircraft from the upstream oil and gas sectors in the Alberta, Canada region are likely to be at least 25 to 50% greater than the current government estimates. So all of these studies indicates the existing of the gap between the inventory estimates and the measurements estimates. So another significant findings from the recent measurements is that emissions vary significantly across basins. So these figures shows the production normalized methane emission rate across U.S. basins. Among all of the U.S. basins, Marcellus Basin and Permian Basin are two largest natural gas production basins, accounting for 21% and 15% of U.S. total natural gas productions. Marcellus Basin is the largest shale source natural gas producing formation in the U.S., while the Permian Basin not only produce a lot of the natural gas, but also a considerable amount of the crude oil. The production normalized methane emission rate in the Permian Basin is 2.9, which is roughly 3 times larger than that in the Marcellus Basin. So this higher methane emission rate in the Permian Basin is associated with more extensive flaring activities in that basin. So after the discussion of the current challenges, we summarized the key points that we have to consider in developing the life cycle analysis model. First of all, the growth in the global LNG trade, as well as the growing climate ambitions, requires us to focus more on the methane emission reductions across the supply chains. In these situations, the life cycle assessment of the LNG supply chains is key to identifying the priority actions for methane mitigation. And second, we have demonstrated that the inventory always underestimates the emissions, though the inventory-based LCA studies are likely to underestimate the supply chain specific emissions. So the methane emission measurements should be incorporated into the current LCA framework. And third, the emission variations across the regions makes it necessary to establish a geospatial specific LCA model for LNG supply chains. Based on the proposed key points, we conducted our study, and instead of conducting the national level LCA analysis, we developed a basin-level life cycle greenhouse gas emission model and quantified the emissions associated with LNG supply chains from US 2 basins to Europe and Asia. So our LCA model consider all the emissions from upstream, processing, transmission, liquefaction, and shipping. And the function unit of our study is 1 megajoule of the LNG delivered at the import country. Then in order to address the underestimation of the emissions in the conventional inventory-based inputs into LCAs, we incorporate the measurements into our life cycle framework. The procedures to incorporate the measurements includes the 3 steps. First, we estimate the methane emission intensities by aggregating all top-down measurement campaigns. And then we aggregate all bottom-up inventory-based methane emission estimates in the process-based life cycle inventories. And third, we compare the inventory-based and measurement-informed emission estimates and add that part of the measurement-informed but inventory non-captured methane emissions to the inventory. And finally, we got the basin-level measurement-informed methane emission intensities, as well as the inventory-based methane emission intensities at upstream and processing stages for both Marcellus to UK and Permian to UK supply chains. At the upstream stage, we found that basin-level measurement-informed methane emission intensities indicates a large disparities between the Marcellus to UK and Permian to UK supply chains. However, the disparities between these 2 supply chains of the inventory-based methane emission intensities is minor. So it further indicates that the addition of the measurements helps us to differentiate different LNG supply chains. And then we will talk about the emission allocation, because all of the greenhouse gas emissions must be allocated to all core products in the oil and natural gas supply chains. So including the liquids separated from the upstream stages and liquids separated from the processing, as well as the final products as the dry gas. So in our study, we employ energy-based and production-assigned allocation method, and our emission allocations are completed at 2 stages. At the first stage, upstream, the emissions are allocated among crude oil, least condensate, and produced gas. And for each individual process, we first identify all the co-products associated with this process, and then we allocate the emissions of this process among all the co-products based on their energy content. The energy content is calculated based on the heating value as well as the production data. And then after the first stage, the produced gas, the raw gas, is transported to the processing plant for further removal of the impurities from it. And the emissions are distributed among processing plant condensate, natural gas liquids, and dry gas, following the similar manner. And because in our studies, we only consider the emission associated with the dry gas, the emissions that is allocated to the produced gas in the first stage should be further allocated among these 3 products. And finally, we can calculate the percentage of the emissions allocated to the dry gas in both Marcellus Basin and Permian Basin, as shown in this table. So in the Marcellus Basin, we find that 97% of the emissions is allocated to the dry gas. But however, in the Permian Basin, only 31% of the emissions are allocated to the dry gas. And this is a figure of the gas energy flow for the Marcellus to UK supply chains. So all of the gas energy loss in this figure is shown in the kilojoule inside of the megajoule for convenience. So given 1,000 kilojoule of the LNG, the one function unit, delivered at the destination port, the amount of the natural gas, the amount of the energy entering each stage is calculated back in a backward manner based on the energy conservation law. And the streams represent the energy loss caused by the methane emission as well as the fuel gas consumptions across different stages, and the downstream flows represent the energy loss caused by the production of the co-products. So given 1,000 kilojoule LNG delivered, in the Marcellus Basin, 12 and 80 kilojoule hydrocarbons should be produced. In comparison, in the Permian to UK supply chains, given the same amount of the LNG delivered, about 40 and 87 kilojoule hydrocarbons should be produced. And we also find in the Permian to UK supply chains, there is a large portion of the hydrocarbon separated from the upstream and processing stages. So based on the established model, finally, we estimated the greenhouse gas emission intensities along each LNG supply chains, as shown in this figure. So here we have 4 LNG supply chains. The natural gas is produced from the Marcellus and the Permian Basin and liquefied at the Sabine Pass liquefaction capacity, and then shipped to UK and China. So in general, the emission intensities between the different LNG supply chains differs a lot. So on the one hand, we find that the emission difference between the LNG supply chains are exporting to the different countries mainly comes from the shipping stage, because the shipping distance from the US to China is about 3.5 times larger than that from the US to UK, because the longer shipping distance would result in the larger fuel gas consumptions and finally leads to more emissions. And on the other hand, the emissions between the supply chain originating from the different production basins differs a lot, with majority of the gap occurring in the upstream stage. And the higher GHG emission intensities in the Permian to UK supply chains is directly related to the higher measured methane emission rate in the Permian Basin. And the higher measured methane emission rate could be explained by the more extensive flaring activities in that region. In this slide, we will discuss about the effect of incorporating the measurements. So this figure shows the greenhouse gas emission intensities of upstream and processing stages for both Marcellus to UK and Permian to UK supply chain. So the dark orange and blue bars represent the inventory-based GHG emissions, and the light orange and blue bars represent the measurement-informed GHG emissions. So before we consider the measurements, the disparities between the Marcellus to UK and Permian to UK supply chains is 7.7 gram carbon dioxide equivalent per megajoule LNG delivered. However, after we introduced the measurements, we found the disparities between these two supply chains increased to 10.4. So which is a 35% increase after introducing the measurements. So it further indicates that the addition of the measurements would help us to differentiate the LNG supply chains sorting from the different basins. And in this slide, we will focus on the methane emissions considered in our LCA framework. So we summarized all the methane emissions into 6 categories according to their sources. Among these categories, the venting, the acid gas removal, the flaring, the fugitive, and the exhaust methane emissions are calculated based on the inventory. And the measurement supplement refers to the part of the methane emissions that is captured by the measurements but not covered by the inventory. So, and also the area of the pie chart is proportional to the total methane emissions along each supply chains. In the Marcellus to UK supply chains, the percentage of the methane emissions that is not covered by the inventory is about 24%. However, in the Permian to UK supply chains, this percentage is even larger, is around 40%. So whether in the Marcellus to UK and Permian to UK supply chains, the percentage of the methane emissions not covered by the inventory is considerable, which further indicates the limitation of the inventory in estimating emissions. And finally, we got 3 key conclusions. First, our established the basin-specific LCA model reveals that the significant emission difference between the Marcellus to UK and Permian to UK LNG supply chains, with most of the significant difference originating from the upstream stage. And then second, with the introduction of the measurements, we can better differentiate the emissions between the geospatial different LNG supply chains and capture more methane emissions. And finally, we found that the methane emissions that are not captured by the official inventory are significant. In the Permian to UK supply chains, it is up to 40% of the emissions is not covered by the inventory. So therefore, we should incorporate the measurements into our current LCA framework to better describing the greenhouse gas emissions along the LNG supply chains. So that's all for my presentation, and welcome questions and comments.